Everybody, this is Randy Compton, All Things Engineering, and what I want to talk about today is the real reason you can't go faster than the speed of light. Now, this is a new channel, so remember to subscribe, give it a thumbs up if you like the video. But some people will tell you in your physics classes it's because as you approach the speed of light, that they talk about relative mass, and it's really relative inertia, and that means that your inertia goes up. So it's harder to push it. But your mass is still the same, but the inertia for the mass makes it harder to push. Now that's so supposedly so it's almost the same equation as this. So what happens is you start getting almost an infinite amount of energy that you need to be able to push it up to the speed of light, a piece of mass. Now, even if you had an infinite amount of energy and you could push, you still couldn't go faster than the speed of light. It would be impossible because it's simply because of this formula over here in the bottom left, and this is the time dilation formula, which is T equals the square root of 1 minus velocity squared divided by c squared. C is the speed of light, so as the velocity approaches the speed of light, what happens is this becomes almost 1. So when you get 1 minus 1, if you could hit the speed of light, it would be 1 minus 1, which is 0. It would be the square root of 0, which is 0. So there'd be no time. Now, that doesn't mean time outside the ship stops. It means the time inside the ship would stop. Now, if you think about this, now a photon coming from our sun, when it leaves, it takes 8 minutes to get here. But to it instantly gets here because there's no time for that photon. Because that photon, it doesn't matter if it's coming from our sun or it's coming from some galaxy 13 billion light years away that the James Webb Telescope is seeing or the Hubble Telescope is seeing. That photon, when it left to it, if you could be on it, there would be no time. It would be instantly because you might see the universe just flying by at an instant, but but that's all you would observe. I mean, you couldn't even observe it because it would all be a Doppler effect out, but you wouldn't even be able to observe it. But there's like infinite, when the speed is like that, there is absolutely no time. Well, the ship would do the same thing. If the ship could get up to that, and you get up to that point, what happens is the speed, your time slows down. So the engines that are running, they're going to slow down. Everything in there slows down. You're going to look like you're in slow motion. So is your engines to the outside universe. Now, you may say, well, okay, I can get it up to, if I keep pushing it, and I get it up to 99.99999 and so on for the speed of light. Well, then you would say, okay, why can't I just get it up to that and it just keep on getting just a little bit more, and it could just get even if you had an infinite amount of energy that you could apply it. Well, the engines are going to keep running slower and slower and slower and slower because the time is going to slow down in that ship. So as you would go, maybe 1 second would be 100 years on Earth. So you've already traveled 100 light years. And as you go even a little bit more faster, it'll give 1 second would equal 1,000 years or 1,000,000 years. And then what would happen is, you've already passed through our galaxy into another galaxy even. So it would never be able to get to it because at the point right before it got to it, the engines would just stop. They would freeze almost. It would take them literally, millions of years to even for the engines to even move 1 second, for you to move 1 second. So that's one of the reasons you can't actually go faster than the speed of light, is because of that time dilation effect. Because it's going to slow everything down. I mean, the ship, everything inside the ship itself is just going to slow. I mean, we know this works. We've got satellites in orbit, and a geo and a geo. Some of the satellites are not geosynchronized. Some are, some are not. But as they fly around, but a lot of the GPS, they're fairly close. If they didn't, they wouldn't be, you know, they wouldn't be overhead where you would need them. So we got a satellite cluster up there. And so these things fly, they're out very far from the Earth. And so they've got to move out 20, if you're in geosynchronous orbit, they've got to be about 20, I think it's around 25,000 miles out. So that thing is moving, to be able at 25,000 miles out, it's in this big, huge circle that it's moving out. It's moving a lot faster than the Earth is. And so we've noticed that when we take an atomic clock and we sync them, and we sync an atomic clock on Earth, and we sync an atomic clock on the satellite, we can tell the difference, because the ones on the satellite slow down. Now, if we didn't use these formulas, that formula right there, your GPS would not even work, because it would get off, I think, about 5 or 6 feet every day. Is about what it would vary. It depends on how far the satellites are out, how fast they're traveling, and all that. But you would lose the ability to have a GPS where you could be able to tell where you're at just in a few days, because it would keep drifting and drifting and drifting, because the time would be so much different. But we know that time dilation formula works. So we know that when you speed a ship up, that the speed inside that ship will slow down. And so if it's slowing down, your engines are slowing down. So, and the closer you get to that speed of light, the slower you're going, till you just can't go any faster. But anyway, guys, that's the video. Thanks for watching. Remember to subscribe. Give it a thumbs up if you like it.